for Jacob. I think you guys should be fine. I think you should be fine. Alright guys, so look up here. Here's me. I'm telling you about the one thing that I didn't have you guys present on. Microwaves are lowest energy, right? Or lower energy. They're not the lowest, but they're pretty low energy. They just cause molecules to rotate. How can you remember that? A microwave makes your food rotate. That little rotation is what's speeding up the molecules inside of your food to make them warm. Microwaves cause molecules to rotate. Do you note that for yourself? That is important on your test. And then second, this was the introduction that I told you guys to make sure you read, but in this case, it's just telling you that every form of matter. AJ, we scooch back some so you can see behind you. So every form of matter can absorb radiation, but the style of radiation, UV, vis, IR, microwaves and radio waves, anything like that, will cause these atoms or molecules to behave differently, and that's what you guys are delineating. How do they behave? And so some of the the different forms of energy will cause the different molecules to vibrate or break apart. I mean, there's going to be different behaviors based on the energy absorbed. And so the different forms of energy, which you guys are going to give us more information on, can just cause an energy state change from ground state to excited state, or cause atoms to rotate. Which form of energy is causing atoms to rotate? Microwaves most predominantly. There'll be some other ones as well. Vibration will come into play, and then electronic excitation just means electrons being excited. That's what you guys are doing. This is your background, okay? So first group up, UV vis. Clicker. Are those lights okay, guys? Laser's the first red button. Alright, so I'm going to try to hit an 8-minute mark because I know that we have a lot of groups to go.
Okay, so
pay attention, guys. Halfway towards your laptop.
we did UV invisible spectroscopy, and so this basically has to do with electrons being excited, like microwaves have to do with electrons like rotating. So quick review, you guys remember that the larger the gap between energy levels, the greater the energy, the more energy it takes to excite the electron. So when light has higher energies, it has higher frequencies, and at the same time it has shorter wavelengths. So that means we're looking at UV invisible light.
Okay, so with UV spectroscopy, the absorption of the light causes the electrons to be excited and move from the lower orbitals to the higher orbitals, as you can see here. And then Kirk and AJ will go into further explanation with this. And then UV will only result in transitions with pi bonding and non-bonding with lone pairs.
That's on molecular scale, which is what we're talking about from here.
Alright, so UV spectroscopy deals with radiation in the range of 200 to 800 nanometers, and these are the various colors. So red has the longest wavelength and the least amount of energy, and UV has, or violet has, the shortest wavelength and the most energy. And there's also complementary colors. So like we looked at this in our labs. So if like a substance is absorbed in the blue range, it appears as orange. And this is how it basically usually works. So you have your light source and it's passed through a diffraction grating or a beam splitter. What that does is it splits the light into different wavelengths or component colors, and then you can measure how much of each light and intensity and what light wavelengths are produced.
So Venki kind of went over like the whole if violet light is absorbed more than it will reflect yellow light. All that can be used. It can help determine structure or like the length of the conjugated polymer, which is something Kirk is about to go over in the next slide. Yeah.
Okay, so conjugated polymer is just a really long chain of carbons that has, it alternates between single and double bonds. You can kind of see that, it's a little hard. But beta carotene is this, and it is a conjugated polymer that absorbs a lot of visible light right there. And
Particularly where? What
Like
was
like green and a little bit of blue maybe.
So between,
Like 400, 500.
that's a great graph to note that specific way of portraying absorption. Keep going.
And a conjugated polymer that absorbs a lot of visible light is called a chromophore. And you may not know this, but you have probably seen beta carotene every day because it is what makes oranges orange. And then transition metal complexes are also like absorb a lot of light or like emit light. And that happens when the d orbitals split when the metal ion is bonding to other things like this carbon hexahydrate right here, where the ligands approach and then the electrons are able to be excited by yellow light.
And this is a great example. Every transition metal, as you guys probably have seen, they many times have colors. Copper 2 is blue. Copper 1 is green. Okay.
Green.
Everything's
Everything's
what
blue.
else did we do? Cobalt. Cobalt. We had that fun with cobalt 2 chloride lab. The Le Chatelier's with some colors that you remember from that. Cobalt was blue and I heard it. Pink, right? So all those transition metals, we say they have colors. That's because they naturally have colors due to this process. Whereas the alkali metals, they only had colors in their process of excitation in the flame test lab. By themselves, they are not colored, but these are by themselves colored because of their d orbital split. Keep going.
That's the end.
Oh, great. So good job, guys. So go back to your absorption. Go back to your absorption.
Yeah, we just.
So at this point, shush, I have very little time with you. My next group with the labs, they're going to reference this quite a bit, the absorption spectrum. You should be able to identify the wavelength that a polymer or a molecule or atom, whatever it is, absorbs at most efficiently, which in this case is beta carotene. It absorbs most efficiently at wavelength 450 or so. That is a good graph to know, okay? So just minimize and then the next group. Escape. You guys are useless. Escape. Go to the next one. Is this it?
Yeah.
Is that you?
Yep.
Okay, hit present. Go. Quickly.
Cool. All right.
All right, listen.
Be on.
If you guys have your laptop open, halfway closed, they give you 2 first strike. They're helping you guys out for review. Go ahead, guys.
Alright, so the molecule takes in light, it jumps from a lower orbital to a higher one. In our example of UV light, since that's really high radiation, it only deals with pi bonds and it jumps from the bonding one to an anti-bonding one. So that means that the molecule must have double or triple bonds. Conjugated systems, this is a system with alternating single and double bonds. So when this happens, ultimately what it does is it makes the entire thing more stable and it absorbs light really easily. That also, when it makes it more stable, the energy gap decreases. So when you have the lower pi orbital that jumps to the pi anti-bonding orbital, that becomes like closer together. Okay. So for absorbance, at the peak absorbance, the wavelength that it corresponds with basically means at that wavelength it's colorless because it absorbs all the light.
Okay, some real-life applications is used to study enzyme kinetics, and enzymes cannot be studied directly, but the activity can be studied by finding the speed of reaction they catalyze. This is used in clinical diagnostics as an indicator of tissue damage. And in the environment, scientists can like take a sample of water and see how much light passes through to see organic materials, heavy metals in the water, and it's also used for dissolution testing of tablets and products in the pharmaceutical industry. Like for example, a tablet is disintegrated to small particles, and limited dissolution is made to make the drug in the solution.
And the reason that heavy water can be tested that way is because concentration is directly related to the absorbance of the light.
Will you guys write that ABC formula here? Is that on your next slide? let's write this down together and just do a quick review of this. I'm helping this group out, so I had them, I threw them to the wolves with the out loud part. Yeah. So big A is absorbance. Big A is absorbance. Labeling for me. Let's do this. Little a is molar absorptivity. Molar absorptivity is a constant that would be given to you for that particular solution at hand. All right, I don't know how you're going to do the next one. B is cuvette length. Cuvette length. And cuvette length is generally held constant as well as like 1 inch or 2 centimeters, something simple. And so if little a is a constant and little b is a constant, C, which is concentration, aka molarity, as they were mentioning with this application in here, concentration is directly correlated to the absorption that the mass spec or the colorimeter observes. So big A and C are directly related because those two, little a and little b, are constants. So we use this in our kinetics lab, as Chloe said. In the kinetics labs, we were all measuring what? What are some examples of things we measure for kinetics? Rate of reaction. Well, how the heck are we using colorimeter to measure a rate of reaction? What were we looking for? Color diminishing. Okay, so we look for the different absorbances over time. So really, we weren't looking at absorbances over time. We were looking at what over time. We measured absorbance to see what. Before I get there, say again. Concentration. So we use the whole absorbance. We've used this light thing to get the concentrations over time. All right, who can remember anything about concentrations versus time? What are different forms of rate laws? Okay, graphs. Let's go. I'm just using these for a moment, okay? Quickly, you guys can. So draw a little graph. Give me 3 graphs. What's the first order? First order, second order, and 0 order. So ln of x. So let's go in order of 0, 1,
Okay,
2.
so
Okay.
concentration.
So concentration versus time. The other way, Ellen. Sorry, my bad. Concentration versus time is our 0 order kinetic reactions, and that's going to be a linear line, positive slope or negative slope. Negative slope, not negative slope. Okay. And then ln of concentration versus time was what? That was our first order, and what kind of slope? Negative. Oh,
It's negative, only positive one is second order.
Okay, on the positive one, second order. And then what's the, 1 over concentration versus time. So those are called integrated rate laws because it's integrated over time. Integration means with time. All right, and then we measured the concentrations through the absorbance. Okay, keep going, guys. Sorry, I'm overthinking them.
Okay, so how it works, basically, you've got this white light source, right? Oh, wait. You've got this white light source, and then it goes into the monochromator, which has like a prism inside of it. So it goes through this little slit right here, and then when it touches the prism, it like diffracts into different beams based on wavelength. And the higher wavelengths are usually at the top, actually, like red, orange, yellow, and then it goes like green, blue, purple. Roy, you did. And then the beams get split into like the faster like wavelengths and the slower ones, and they get recorded by the detectors, and then using this process can determine like it kind of like measures the rates of the like color change.
Which would give us kinetic information.
Gives us
Nice.
kinetic information. Yeah. All right. So the diffraction of the white light, kind of like explaining this further. So it enters as a single beam, and then it escapes as the multicolored ones, and then those can be recorded based on wavelength, giving us that kinetic information. That's it.
So with that, this is done before all the kinetic experiments are done, because they actually have to see which that particular compound C. We need to know its absorption spectrum first. So go back to your first slide. So that's first slide. Right? Oh no, sorry, second slide. No, so we would run every wavelength. I'm just in the lab. It took me forever, but you would run every wavelength to see which wavelength was the best or the optimal absorbance. And then you get this graph and you go, this is the wavelength I should use. And so when you do partition your light, you say, this is the wavelength I need to use to get the maximum observance, and then I would run all my testing on that. That's why I told you guys to go blue chlorine or blue Kool-Aid lab. I was like, you have to use red, you have to use 650 wavelength. You have to, because that was going to give you the best data. So I did all your pre-work for you for your absorptions. Nice, great, keep going, guys. Let's go with our usual. You get IR. IR. Escape. All right, we have 7 or so minutes on this one. This one's a really interesting explanation one. Okay. All right, so if you guys could start. There we go. Where's the clicker? All right, this is new information. This has never been seen before. Never been seen before. Go.
We had infrared spectroscopy. So it's the analysis of infrared light interacting with the molecule. So it pretty much just vibrates the bonds inside the atom. It detects the absorption of various samples with the wave number. The wave number is the waves per unit distance, per 1 unit distance, and it's proportional to energy and frequency.
Everybody get up. Show us what you're doing.
Oh my gosh.
Explain it as we go, okay? Stand up.
So basically, well, she's gonna have you do something weird. But what happens with your molecules is whenever they absorb infrared energy, they're already vibrating, but this causes them to first off vibrate more, which is what you see here. And you want to go ahead and do that. That'd be a good
Yeah, we're ready. So you B carbon dioxide, B it. Okay, and so we absorb energy. We absorb the IR, which is a low frequency energy, and what do? Well, come on, Levi. Let's go.
Alright, so like your ligands are gonna start like moving around.
Okay, and then we are.
And then alright, so sometimes they have stretches, so they're either gonna like come, yeah, whatever she's doing.
Symmetric stretching, yeah. So symmetric arms, okay. And then sometimes what?
Oh, asymmetric, so they're gonna go unevenly and be stretched different ways to create dipole moments.
Okay, and then?
They're stretching, they're going all around.
So these are the stretches, and then these are the bends. Bends. A little workout today, guys. And then sometimes you have to vibrate on the x-axis, and then the y-axis, and then the z-axis. So there's a variety of reasons why these stretches and these bendings would occur. Okay, sit down, keep going.
Okay. So the more energy that the molecule absorbs is proportional to how far it's stretched. If it absorbs just a little amount, it's probably the thing has things about like a spring, so your spring's just gonna kind of bend. If it absorbs more, it's gonna actually stretch out. And then also the stretching has to do with what type of bonds you have. Triple bonds are going to take more energy to stretch farther as compared to single bonds. And also the mass heavier ligands, I want to say, so like if you have chlorine and
Hydrogen.
carbon as opposed to carbon and hydrogen, yeah, the chlorine is going to stretch farther with the same given energy just because it's heavier.
So it's like a weight on a slinky. It's very heavy, so it's stretching out.
Okay, so it's used to help determine the structure of an atom and determine functional groups and specific bonds because, like Levi said, each bond kind of has a different vibration. So, like, you'll have this red one with that, and then
What's the red one representing? OH?
Okay.
That red thing's an OH?
yes.
That's ethanol. So it's representing OH, so that's a big long stretch. What about the other one, the yellow one?
The yellow one, I think it's carbon to carbon.
What's the other end? Yellow is carbon to hydrogen.
Yeah,
right?
that's carbon
I'm
hydrogen.
looking at the structure. That's blue.
Yeah, that's oxygen.
We're looking at yellow.
Okay, yeah. So that's carbon to
So the yellow one's carbon hydrogen, the blue one's what?
oxygen.
Carbon oxygen. Right, so specify the lengths there. So the red one stretched the longest, right? Where's the yellow one on the graph?
It's a little bit less.
A little bit
It's
less.
like it's very small right here.
And then the blue one is
Yeah.
I'm going to pause for a second. So this is a really interesting factor because UV vis didn't tell us a whole lot about the structural functional groups. UV vis is just like, I have a lot of conjugations. Look how much light I absorb. Look how much light I give off once I do absorb that. IR is like, here's the strength of my bond because I take a lot of energy to stretch. Here's the style of bond I have, and this is what I contain within it. But it does this without destructing the molecule. Keep going.
So in the real world, it's used to identify the structure of molecules in space, and it's used to determine the timescale for folding complex proteins into biological molecules. And it's also like a breathalyzer is basically an IR spectrometers, and they read like absorptions of about 1060 per centimeter, and they read the vibration corresponding to the CO bond of ethanol, and that's like a diagram showing how it works. So there's just like a red beam that goes through, and
It affects the molecule.
yeah.
So you breathe into the breathalyzer, you put in your carbon dioxide and ethanol saturated breath in, and then they shine the IR on the molecules, and they react to that light, so they vibrate or they stretch, and then there's a reading that comes out and tells the police officer whether you're toxic or not. Okay? Awesome. Good job. I'm going to pull that other graph up, so I want to show you guys that in depth. Yeah. We got one more presentation. Can you wait? All right, let's go. Oh, no, I'm going to show the other graph at the end. Last group, let's go. Can you pull up mass spec, the in the middle, the one that says M? Yeah, thank you. All right, guys, I have 5 minutes left with you. Let's roll.
Oh, nice. Okay. So we have mass spec. What is it? So it provides molecular info on molecular mass and structure of atoms. It's very sensitive, so it uses very small measurements because the atoms are so small. And there's 5 stages. I'll explain that later. And basically, once it's all said and done, you determine the deflection based off of the mass and the charge of the atoms. And the lighter the mass, the more deflected it is, the greater the charges, the more deflected it is. And then you do a mass to charge ratio. And if the ratio is smaller, the deflection is larger. And then you can use this to determine the relative abundance of, for like isotopes and stuff. And so, look at this chart over here.
Remember those mass spec charts? Percent abundance. You don't go back to each one.
And so here is our chart, our graph, not graph, our chart. So you have vaporization. If it's not already gassed, it converts it to gaseous form. Oh shoot. And then ionization. They use an electron gun to ionize, and then they're accelerated in the electric field, and then deflected by the magnet. So the first line right here, this one would be the atoms with the lighter mass and the greater charge because they're deflected more, and then this one would be heavier and smaller charges. Yeah.
Okay, so one.
Oh.
How it's applied, it provides relative info about molecular mass and structure.
Okay, it can analyze very small structures, even a few nanograms.
So the first example is liquid chromatography, and pretty much what it is it separates complex mixtures with capillary tubes, and the most up-to-date tubes are like 100 micrometers in diameter, so you can put a very small amount in there, and that's really helpful because mass spectrometry actually destroys the sample. And then so some applications of liquid chromatography would be proteomics, which is the study of proteins and digestive products, pharmaceutics, which is like drugs and then analyzing of drugs, and environmental, which is like analyzing herbicides and pesticides in the residue and fruits.
Okay, so next is gas chromatography, and it is basically measuring inert gases and mobile phases that can be separated out of a mixture. And gas chromatography is mostly used in airport security, basically, which is a big one, which is basically where they look at whenever they're going. Basically, when you walk through like TSA and you're going through and you're getting all in your bags and stuff are getting all checked, they can use gas chromatography to check for like drugs or stuff like that, or for like bombs, and then also fire forensics and industrial chemistry.
High resolution, it can distinguish compounds with same nominal mass but different actual masses, so things like ethane, formaldehyde, and nitric oxide. You guys got it.
Go. Next slide. Great. Gas, liquid, and then the other one.
Nice. There you go.
Okay, so I'm gonna skip to the cool one, drug testing. It's obviously used to test for drugs in person's system. They commonly use urine testing, and it's kind of gross. They use gas chromatography, so they like.
It runs your pee?
Yep. So this is normal urine sample, and then this is like with drugs in the system, and so they measure like how much of the drug is in the system and like what kind of drugs are in your system. And in this case, it's steroids. I don't know if that's a type of drug.
That's go for it. Alright, and oh my goodness, thank you guys. Alright, let me have you guys log off, and then at this point, I think you probably want to go back and look at some more of the examples on the humongous 87-page document. But you want to just look for the key points. Okay? I will update the website and you show it for yourself for tomorrow. Bye. I'll link them all in the homework. I'll link all the presentations under homework. Today is Thursday. Today's Thursday. Yeah. Okay. Oh, my fourth period. Okay.